My topic is deterministic and probabilistic case analysis of slopes. I'd like to mention a few words about probabilistic and deterministic. Probabilistic analysis differs from deterministic analysis in explicitly accounting for some uncertainties. For example, the uncertainties of the input values. We can regard probabilistic analysis as an extension of deterministic analysis because the slope stability methods such as limit equilibrium and also finite element method used in deterministic analysis also needed in probabilistic analysis. This one I will skip. You can look at it later. And this one about my book, you can also look at it later. Right. About this webinar, we will be looking at a deterministic analysis and a probabilistic approach, which is called reliability analysis, which account for input uncertainties and also can give sensitivity information on the underlying parameters. I'm supposed, let me see. There's a pointer. That's better. Right. We'll be looking at the slope in San Francisco Bay Mud that failed, and also a slope in Steve Fisher London clay that failed, as well as a Norwegian slope involving anisotropic and spatially autocorrelated shear strength. And then look at the zone of them with a sloping clay core, which came from Lamb and Whitman, a deterministic case, which will be extended probabilistically. If time permits, I will then move on to the Hong Kong rock slope with discontinuity planes. Right, the LRFD, I think those engineers in the US are very familiar with it. The main idea is then the sum of the factored loads is equal to the factored resistance. So then the set of value are then called the design point values. So you have factored values of loads and factored value of resistance. Form stands for first order reliability method, which can be extended, as I'll show later, into second order. And form also has a design point. However, the form design point reflects parametric correlations and case-specific sensitivities in a way that the LIFD factors cannot reflect. For example, then the LIFD design point is somewhere here or here. It may not be the same as the form design point. The average point is the mean value point, and these ellipses are contours of equal probability. You can imagine there's another axis perpendicular to the plane, which is the resistance. I showed this just now. The case was negatively correlated load. Now then we have a positively correlated load. The higher loads in the upper domain are the unsafe region. And then although the mean value point is safe, we are interested to know where is the most probable point of failure. So as the ellipsoid in higher dimensions expands, eventually it will touch the limit state surface and give you the most probable point of failure, also called the design point. And this perspective is also valid if you have a non-Gaussian random variables regarded as equivalent hyperellipsoids. And keep it, bear in mind that the reliability-based design via the first order reliability method does not require nominal values. Also does not require load factor or resistance factor. However, from the design point that you obtain in FORM, you can actually back calculate LF and RF for comparison with LRFD and to provide insights to LRFD. This is just to highlight some limitations of the traditional overall or lump factor of safety approach. You may have two cases, case A, case B, both having overall factor of safety 1.6. But as is clear from here, case A is the more reliable one because it will expand further to touch the limit state surface, the most probable failure point. Whereas case B then will touch it right with a little bit of expansion. So this is a more risky case, despite the same factor of safety. Another example is you may have a case with factor of safety 1.5 for slope and 2.5 for foundation. Although the factor of safety 2.5 and 1.5 are different, they actually may denote the same reliability with respect to the mean value point to the limit state surface. Now then we come to the first case study, the underwater slope failure in San Francisco Bay Mud. This was a case discussed in Duncan JM 2013. Also in the book, earlier book by Duncan and Wright, 2005. And then I wrote a paper with Mike in 2013 and to extend it into probabilistic analysis. And this is also described in more detail in my book. Now, deterministic analysis, all of you have this familiar experience. Pass the fitted line through the scattered points and take that line for design and analysis. That is deterministic analysis without explicitly accounting for uncertainty. And there is another complication in this situation here. The data points actually valid only up to about 2/3 the depth from the top mud line. 2/3 depth for a circular surface is actually then about at the midpoint of the slip circle. And therefore, then you can see then this portion of the slip surface actually is based on extrapolated values. And it's interesting to note that if you include the bad points, the lower portion of the fitted linear trend actually is higher than the black dash curve, which exclude the bad points. Anyway, the factor of safety for circular and non-circular surface. Non-circular is slightly lower. And also you have the paradox, apparent paradox. How come excluding two low bad values, or rather including the two bad low values at the top, you end up with higher factor of safety because of the extrapolation. So bias in strength measurements and interpretations can cause factor of safety calculation, disturbance effects, rates of testing, extrapolation of measured strengths to greater depths. We saw just now that there were three types of tests, the field test, as well as tracer test in the lab with the external portion trimmed off to reduce disturbance. And 70 mm is the original diameter. So then they will give a different factor of safety. Now, come back to the extension from deterministic analysis to probabilistic analysis. We would like to explicitly account for uncertainty. So in that case, we like to consider the scatter of the data points. And then you can then analyze and then put up two standard deviation lines, plus and minus one standard deviation. And the probability of failure based on reliability index is shown on this slide. It goes from 10% to 40%, depending on whether you are using the untrimmed triaxial specimen, 70 mm original diameter, or whether you are using the trimmed 35 mm diameters, presumably with the disturbance reduced, or whether you are using the field vein test. The factor of safety goes from about 1.02 all the way to 1.23. the probability of failure is high, from 10% to 40%, regardless of the type of test you use. In reliability-based design, the 10%, the ultimate limit state such as stability issues, we would like to keep the probability of failure below 1%, which corresponds to reliability index greater than 2.5. And therefore, then these three values of probability of failure all imply that reliability index is smaller than 2.5, therefore unacceptably high probability of failure. And no wonder then a section of the slope actually failed. We next look at I'm looking at my watch, not try to finish in time. Okay, you have an excavator slope in London clay that failed. If a stiff Fisher clay and the 14.8 meter and the slope failed about 5 days after excavation. And what did the deterministic analysis show? Very high factor of safety, about 1.8. So deterministic analysis pass a fitted line through the scatter points, so-called mean CU value. Based on mean CU value, you do the critical slip surface search, you end up with factor of safety 1.8, and which is considered quite high. But if you do to extend the deterministic analysis into probabilistic analysis, you would like to consider the scatter or the uncertainty of the data. And in that case, you have the plus and minus 1 standard deviation boundary. And from there, you can then do reliability analysis. Now, look at the deterministic case first. Sorry. Right, I said, based on a single fitted line, you have Fs equal to 1.8 using mean CU value, which is high, and yet the slope failed about 5 days after excavation. This is London clay, stiff and fissured. And triaxial tests in the lab on small specimen may not capture the fissures. Plate loading tests at the sites, larger volume being tested, can include some of the fissure effects. And you can see then the implied undrained shear strength. Is this the top blocking the label? Anyway, the screen, okay. Now, this actual value of undrained shear strength, including fissures, would be lower than the small specimen. So then if you then have a reduction factor on the CU, which can go from the unreduced one of 1 all the way to 0.9, 0.8, 0.7, 0.6. Deterministic analysis will then give you factor of safety close to approaching 1, although the unreduced factor of safety is 1.8. Reliability analysis, if you do not reduce the fissured strength, you end up with a reliability index above 2.5, which is considered adequate. But the moment you have reduction 0.9, 0.8, 0.7, 0.6, the reliability index becomes unacceptably low. Right. This is a case of clay slope in southern Norway, and with specially autocorrelated shear strength in the horizontal direction, as well as a unit weight. Therefore, there's a variation of a shear strength horizontally, and with that also the an anisotropic shear strength depending on the angle of shearing. An interesting thing about this case is then since we treat the unit weight as a spatially autocorrelated, just for the case where the autocorrelation distance of 10 meters, which is the typical, you actually have a unit weight in this region smaller than mean value, whereas unit weight in this region higher than mean value. And you can understand that by noting that this actually is the resisting zone for this slope that tend to fail this way. And you can verify by deterministic analysis. Using smaller unit weight, you end up with a smaller factor of safety. Higher unit weight, you end up with higher factor of safety. So this sensitivity is shown automatically in the reliability analysis. This sloping core dam from Lam and Whitman 1979, deterministic analysis, which I extended probabilistically. There is undrained shear strength on the clay core, and there is a frictional resistance through the granular shell material. And you actually can then search for the critical bilinear slip surface. This first slip surface going through the dash lower line is not the most critical. It has a slightly higher factor of safety. If you search, you get a 1.603, which is the more critical. And reliability analysis actually indicate that the friction angle in the granular shell material is a much more sensitive parameter compared to the undrained shear strength on the clay core, where the upper part of the slip surface passes. So this context-dependent sensitivity is automatically reviewed in a reliability analysis. By the way, this is adequate reliability and adequate probability of failure adequately low. So this is a satisfactory situation for the mean value and standard deviation. Mean value is based on the Lam and Whitman mean value. Standard deviation, I took it to have some typical coefficient of variation. This one is the Spencer method non-circular slip surface, starting from 4 initially arbitrary circles. You can then converge into a non-circular, quite close to each other. This one, I won't go through in detail. You can read my book if you're interested. This is the Hong Kong slope case, a rock slope with discontinuity. You have a tension crack, and then you have a joint. And therefore, then the block can potentially slide along this joint plane, and unfavorable water pressure in the tension crack, and also along the joint plane, and also then the earthquake effect, horizontal acceleration alpha, and the input values, normal, trim exponential, then based on earthquake, practical rock engineering, but he did a Monte Carlo simulation. I did the first order reliability method and second order reliability method for comparison. It compared very well. So then Monte Carlo, in this case, with the force, the rock ball force required to achieve a reliability index of 2.5. And then going to the SORM is a 0.32% average failure probability. And this compares very well with this Monte Carlo simulation. And then a load factor and resistance factor can be back calculated from the design points of RBD via form, reliability-based design via the first order reliability method. And you have a load factor which varies with reliability index. The same with resistance factor. Also, it depends on what nominal load you use, whether it's the more conservative load of mu plus standard deviation, or the less conservative, the average load. This case is also quite interesting from Richard Goodman textbook. And it has 2 blocks with this two discontinuities. Therefore, you have a block 1 up there, block 2 here. Block 1 has weight W1, W2, and then you have a friction angle phi1, friction angle phi2. Interesting thing is that despite the same nature of the friction angle and the same mean value, same standard deviation, they have a different sensitivity. The friction angle of the lower block actually is a more sensitive parameter compared to the friction angle of the upper block. Likewise, for the weight W1, W2, which depends on volume 1, volume 2, this sensitivity indicator says then critical condition is reached when weight 1 is increased, but weight 2 is reduced. So it's a different scenario even for different context-dependent sensitivity. I won't go through this. This is a more complicated case. Three-dimensional wedge is in my book, if you are interested, sliding along both planes 1 and 2, sliding along plane 1 away from plane 2, another mode, sliding along plane 2 away from plane 1, and contact is lost on both planes of floats. Compare well with the sequential vectorial procedure described in Hoek and Brown's book, or Hoek and Bray's book. Coming to the end soon, FORM, FORM, stands for the first order reliability method. Can I close this thing? Anyway, system form, multiple failure modes, SORM, second order reliability method, and then you have a response surface method. Form can be extended into system form, SORM, response surface method to analyze with finite element method and finite difference method, and also important sampling at the design point. In what way can reliability-based design complement partial factor design methods like Eurocode 7 and also LRFD? Here then I have this, including the output has different context sensitivity to an input parameter depending on the engineering problems. And when input parameters are by their physical nature either positively or negatively correlated, that means even for LRFD, load 1 and load 2 may have a correlation, and their correlation may affect their sensitivity. And when soil rock properties are spatially autocorrelated. And also then you can have explicit target reliability index and probability of failure instead of LRFD, which does not convey information on probability of failure. So then in this way, then reliability-based design can complement LRFD and Eurocode 7. I say complement, not replace, because Eurocode 7 and LRFD are easier to use for practitioners and easier for them to understand. Come to the last slide. Yes, the cases I discussed just now can be found in chapter 8, 9, 10. Chapter 8 is on soil slope stability of my book, published last month by the CRC Press. And the rock slope stability, 2-dimensional, 3-dimensional, can be found in chapter 9 and 10. So then for participants who are interested, you're welcome to take a look at the book. Thank you. And I think I should reserve a few minutes for question.
Great, Bak Kong, thank you for an excellent presentation. And we do have a couple questions I hope I can squeeze in here. First, can you comment on when you would choose to use stochastic distributions rather than Monte Carlo simulations for assessments?
The Monte Carlo, if you meant by stochastic simulation means the reliability approach, reliability analysis, and reliability-based design, as opposed to Monte Carlo simulation. Yes, there's a difference. In Monte Carlo simulation, you can get a probability of failure, but you may not have the insights and interesting information relating to the design point, where the expanding dispersion ellipsoid touches the limit state surface. That point, the design point, or most probable point of failure, give you information about parameter sensitivity, which is context dependent. Parameter A may be sensitive in this case more than B, but in another case it is B more than A. Monte Carlo simulation. So then Monte Carlo simulation The one that I'm familiar with, I can give you probably the failure. But I think as engineers, we also like to know, can we know something about the sensitivity of the parameters as reviewed by the design point?
Yeah, I don't know, Bak Kong. That was the whole question there.
But the other thing that you mentioned, stochastic has another meaning, which means spatial autocorrelation. That is the relevant and can be modeled also in Monte Carlo simulation, spatial autocorrelation. Come to think of it, if we have a long stretch of slope, soil slope, are you saying then if I know the unit weight at one point, the unit weight everywhere is the same? If not, then you may want to model it as a spatially variable property with autocorrelation.
Okay. Let me try to squeeze in one last quick question. You noticed in your analysis of the strength parameters, you used 1 sigma or 1 standard deviation off your average trend line. In Mike Duncan's 2000 paper, he uses the 3 sigma rule, or 3 standard deviations off to get the highest likely value and the lowest likely value. Why did you choose only 1 standard deviation?
Mike, the book and the paper, yes, mentioned that very interesting and useful 3 sigma rule. What it means is then when you know the highest perceivable value and the lowest perceivable value, you can take it that the 3 sigma left and right will include about 99.87 of the values. And therefore then with that 3 sigma rule, if the distribution is symmetric, you can then take the highest perceivable value and the lowest perceivable value, the range, divide by 6, you get the standard deviation. In the second edition of the book I read, they also suggested that sometimes practitioners may wrongly estimate the range too low. In that case, the range will be 2 sigma on either side. Then you will take the range divided by 4. Is a useful and convenient way, one way, if the distribution is symmetric. Yes.
Okay. Great, Bak Kong. Thanks so much for joining us from Singapore and giving us an excellent presentation on reliability.
Thank you, Tim. It is 3:30 a.m. in the morning.
Thanks for staying up late or waking up early for us, Bak Kong. See you later.